Hello, my name is Mohammed Adib, and I'm a PhD student in Carleton University in Canada. Today, I will present a simple model to describe surface growth, coagulation, and oxidation of soot particles. Morphology of soot particles is important for climate models and carbon black reduction. Sectional population balance models and discrete element modeling can accurately predict soot morphology, but they are computationally expensive and difficult to interface with chemical kinetics and computational fluid dynamics. Here, we propose a simple three-equation population balance model that tracks number density, carbon content, and surface area of particles, accounting for their fractal-like structure to predict coagulation, surface growth, and oxidation. The model calculates primary particle diameter in agglomerates using particle mass and surface area, and uses the scaling laws from DEM simulations to account for the evolving fractal-like structure of agglomerates by calculating their mobility and gyration diameters. At high particle concentrations, where inception and surface growth are short, self-preserving size distribution and asymptotic fractal-like structure are rapidly achieved, and tracking average properties is enough for monodisperse models to have accurate predictions. Often soot particles are approximated by spheres having the same volume as fractal-like structure. Here, we evaluate the impact of such an oversimplification on simulation accuracy. We also benchmark the proposed monodisperse model with measurements of the premixed flame. As the measurements and DEM simulations show, there is an initial sharp increase in primary particle diameter at the beginning where surface growth is predominant. Then it levels off and reaching its final value of 9.5 nanometer. The monodisperse model accurately predicts the primary particle diameter in excellent agreement with the experiments and DEM results. On the other hand, the mobility diameter continues to increase due to agglomeration. Higher mobility diameter is associated with larger agglomerate structure with more primary particles. Monodisperse model again accurately predicts the evolution of mobility diameter. However, a spherical particle approximation does not take into account the fractal-like structure, and it overpredicts the primary particle diameter by a factor of 2 and underpredicts the mobility diameter by 40%. The number density of particles decreased by coagulation in agreement with the measurements. The monodisperse model accurately predicts the number of agglomerates following the measurements and detailed DEM results. However, spherical assumption overpredicts the number of particles, which is expected because spheres have a smaller collision diameter compared to agglomerates, resulting in lower collision frequencies and weaker coagulation. Volume fraction sharply increases and it reaches its maximum value if the surface growth ends, which is accurately predicted by monodisperse model. Since surface growth is rapid, it happens in a region where agglomerates are very compact and sphere-like, the model approximating agglomerates with spheres also predicts the volume fraction accurately. In conclusion, we presented a three-equation monodisperse model that accurately predicts important soot characteristics during surface growth, agglomeration, and oxidation. Thank you.